Hello, chemistry students. Welcome to the start of your notes on Chapter 8, Section 3. We're going to talk about net ionic equations a little bit today, actually kind of a prelude to net ionic equations. So this section is called Reactions in Aqueous Solution. Remember, we've talked about this term aqueous before. Aqueous means that the substances, the ionic compounds, are dissolved in water. So, to kind of start talking about net ionic equations, you will typically be asked to do a net ionic equation for double replacement reactions. So these are usually double replacement reactions, but it can be a single replacement. Most of the ones you'll do will be double replacement, but it is possible that you could be asked to do a net ionic equation for a single replacement reaction. Now, again, kind of thinking about especially our double replacement reactions here, okay? So thinking about those double replacement reactions, remember that double replacement reactions must produce something so that we know that they've taken place, right? And there were kind of three choices. They must produce a precipitate. Remember that a precipitate was a solid, so it's when I have two kind of look like liquids, right? Because they're ionic compounds dissolved in water, okay? And I mix them together and I get a solid produced. That's a precipitate. They could produce a gas. We would know that they've produced a gas because there's bubbles. Or a molecular compound. Which is usually water. Okay, so something has to happen when I have these reactions happening in aqueous solution so that I know this reaction has taken place, okay? And again, we're going to get that precipitate, which is that solid. We may get a gas, we'll see bubbles. Or, and this one's harder to see happen, but when we balance our equation, we would see it. We have a molecular compound produced. Now, ionic compounds, which are the kinds of compounds taking place in a double replacement reactions, dissociate in water. So dissociate might be a word that you've not heard before. Kind of can use it in a more everyday sense in a sentence. So in the mornings before school, when students are standing in the lobby, if two friends have had a disagreement, they may dissociate from one another. Okay, so again, dissociate sort of means to break apart or to move apart. And what we're seeing here is these ionic compounds are dissociating in water. What does that mean? That means that these compounds break apart into their ions when they're dissolved in water. Remember, being dissolved in water, we call that the state of matter of being aqueous. So if in our reaction they mention that our compound is in aqueous solution, that means that that compound is dissolved in water, and those cations and anions that form that compound have broken apart and are now kind of floating around separately within that water. Okay, so again, we're going to be doing net ionic equations. Mostly, you'll be doing them for double replacement reactions, but you could be asked to do one for a single replacement reaction. Remember that something has to happen for double replacement reactions for us to know that they've taken place, because again, they're taking place in that aqueous solution. So we're going to have a precipitate form. That means we have a solid produced. We have a gas produced, so typically we're going to see bubbles, or we have a molecular compound produced. And again, oftentimes you're not going to be able to see that there's a molecular compound. You're going to discover there's a molecular compound when you look at your balanced equation. So these ionic compounds that we're going to be talking about, and these double replacement reactions, these ionic compounds dissociate when they're dissolved in water. What that means is the compounds break apart into their ions, their cation and their anion, when they're dissolved in water. So anytime that the state of matter is aqueous. So the first thing we're going to do in the process of trying to get to a net ionic equation is we're going to write what is called a complete ionic equation. The definition of a complete ionic equation is equation that shows dissolved ionic compounds as free ions. So again, what we're talking about here is we're talking about these ionic compounds that are dissolved in water, and because they're dissolved in water, they have dissociated. So instead of showing them as a compound bonded together, we're going to show these ionic compounds as their separate cations and anions, or as their free ions. One really important thing about complete ionic equations, you must include the state of matter on every element, compound, ion. Okay, so remember, up until this point, I haven't cared a whole lot whether you were including states of matter. When you're just asked to write and balance a chemical equation, I don't care if you have those states of matters in there. However, if you're being asked to do either a complete ionic equation or a net ionic equation, then you must have the states of matter. So again, we show these states of matter as subscripts. So for a solid, it's an S. I use a cursive S so it doesn't look like a 5. For liquid, it's an L. For gas, it's a G. And again, we're going to use aqueous quite a bit. It's an AQ. So for example, water, okay, is a liquid at room temperature. So we would write water, H2O, liquid. Another example, oxygen gas at room temperature is a gas. So we would do a G. Okay, so again, when you're doing a complete ionic equation or a net ionic equation, you have to include these states of matter. So we're going to take a look at an example. And again, we're going to start with that sentence as always. So our sentence for this one is that silver nitrate reacts with sodium nitrate Sorry, shouldn't be nitrate, so I got to fix that. That did seem a little wrong when I read that there. With sodium chloride, both in aqueous solution. Okay, so again, I want to do my word equation first. So again, silver nitrate reacts with, becomes my plus. We have sodium chloride as our next compound. And again, right now in my word equation, I can kind of leave that aqueous solution part out. We'll kind of add that in when we get to writing and balancing it. So again, next we have our arrow. Now remember, to predict the products, I need to be able to identify this reaction as one of my 5 types. I have a compound reacting with a compound, so that's a double replacement reaction taking place here. And in double replacement reactions, the positively charged ions, or the metals, swap partners. So in this reaction, silver and sodium are going to swap partners. So silver is going to be one of my products, but its partner now is going to be chloride. And sodium is one of my products. Okay, and sodium's partner is going to be nitrate. So we'll go ahead and write a balanced chemical equation for this. Again, these are all ionic compounds, so every single time I'm going to do symbols, charges, crisscross, lowest whole number ratio. My symbol for silver is Ag. Okay, it has a charge of +1. Nitrate is NO3, -1, so nothing to do to that one. Sodium is Na, its charge is +1. Chloride is Cl, charge of -1. Silver is Ag. On your helper sheet, it has only one possible charge of +1. Cl, -1, nothing to do. Na, NO3. Right, so this would be my balanced equation. When I look at balancing this, 1 silver, 1 silver, 1 nitrate, 1 nitrate, 1 sodium, 1 sodium, 1 chloride, 1 chloride. This happens to be a skeleton equation that's also a balanced equation. So to give myself a little bit more room, I'm going to rewrite that skeleton equation here again and that balanced equation. So I have AgNO3, and I'm going to go ahead and put that aqueous behind it, plus NaCl aqueous produces, okay, and we had our AgCl, and I'm going to tell you right now that that's a solid. Before we're finished with our next part of our Chapter 8, Section 3 notes, you'll learn how to know that for yourself. But for right now, I will just tell you that it is. Oops. 3, and again, this is aqueous. Okay, so this is my skeleton equation. It's also my balanced equation. We just kind of went over that. So what I want to do now is I want to write that complete ionic equation. So again, kind of reviewing our definition of our complete ionic equation, it's an equation that shows the dissolved ionic compounds as free ions. What that means is anything that has this aqueous state of matter, I'm going to break apart into ions. Aqueous going to break apart into ions. This one's a solid, so I'm going to leave this one alone. I won't do anything to that one because it doesn't break apart. This one's aqueous. I'm going to break it apart. Okay, so here's what my complete ionic equation for this reaction looks like. Again, when I do my complete ionic equation, a couple other things to keep in mind. Okay, we have to have our symbols we have to have charges if they're ions, and we have to have a state of matter for everything. Okay. So, again, I know that silver is going to break apart into Ag plus 1 aqueous plus NO3 negative aqueous. So that's just taking that silver nitrate and breaking it apart because it was in an aqueous state of matter into its ions. Same thing with sodium chloride, so Na plus aqueous plus Cl minus aqueous yields. Now, again, I don't break apart the silver chloride because it's in the solid state of matter. So I'm going to leave my silver chloride as is, but my sodium nitrate is aqueous, so I'm going to break it into its kind of products or ions. So that's a sodium ion with a plus 1 charge aqueous and a nitrate aqueous. So that is my complete ionic equation for this reaction. So again, I have silver ion aqueous reacting with nitrate ion aqueous, reacting with sodium ion aqueous, reacting with chloride ion aqueous, producing my silver chloride that stays a solid, so I leave it written together as a compound, and sodium ion aqueous and nitrate ion aqueous. So that is where we're going to stop. Oh, nope, I guess it's not quite where we're stopping for today. Okay, so now that we have this complete ionic equation, the next thing we want to do is identify who the spectator ions are. Now, to kind of help you think about this again, think about the word spectator. What do spectators do at a football game? What do spectators do at a wrestling match? What do spectators do at a basketball game? What do spectators do at a quiz bowl meet? Right? Spectators, they're watching, but they're not really participating in the event, okay, in any meaningful way. Spectator ions are the same thing. Spectator ions are the ions not directly involved in a reaction. Now, how do we know that they're not directly involved in a reaction? Because these are the ions that appear in the exact same form So again, here with form, we're talking about symbol, charge, and state of matter. On both sides of the equation. Because these ions appear in the exact same form on both sides of the equation, these spectator ions are not really participating in the reaction. So we can leave them out. And tomorrow when we talk about writing a net ionic equation, that's what we're going to do. Today, we just want to identify them from our example. So if we go back and look at our example here, okay, we're looking here at, again, our complete ionic equation, and we're looking for our spectator ions. We're looking for these ions not directly involved in a reaction. These are ions that appear in the exact same form. So their symbols, their charges, their states of matter, okay, are exactly the same on both sides of the equation. So if I start by looking at silver, I have Ag plus aqueous, and silver is in a compound over here, so silver ion is not a spectator ion. Nitrate, NO3, -1 aqueous, okay, right here, and then NO3, -1 aqueous. So nitrate is a spectator ion. So one of the ones I can identify here is nitrate. Okay. Sodium, this should be, that is a plus, just to make sure. So sodium is Na plus aqueous, and we have Na plus aqueous. So sodium is also a spectator ion. Now remember, I have to call it sodium ion. Otherwise, if I just call it sodium, it's a neutral atom. Let's take a look at chloride. I have Cl, -1 aqueous, and here it's in a compound. So chloride is not a spectator ion. So my spectator ions in this reaction are nitrate and sodium ion. So notice here, I have two different ways that you can identify them, and you only need to do it one way or the other. You can write their names, making sure if you have a metal that you include the word ion because it has to have a charge, or you can write the symbols with the charges. I don't care which way you identify spectator ions, either way is fine with me. So that brings us to where we're going to stop for today. Notice that you don't have any homework today, so it's a good day to make sure that you're caught up with everything in chemistry right now. Have a great day. Talk to you tomorrow.